morning. This is a stochastic process model 4 discrete time Markov chain, and this is the lecture 2, and in this lecture we are going to discuss about the Chapman-Kolmogorov equations. Then we are going to discuss a n step transition probability matrix, and we are going to discuss a few more examples in this lecture. In the last class we have discussed the transition probability of j to k in n steps as the probability that the x m plus n takes a value k given that x m was j for n is greater than or equal to 0 and I comma j belonging to S. Since the underlying DTMC is a time homogeneous, this is the n step transition probability of system is moving from the state j to k in n steps. So, this we denote it as a conditional probability of p j comma k in n step transition probability, where I comma j is belonging to S, where S is a state space and n can take the value greater than or equal to 0. Also we have discussed in the last class what is the one step transition probability of p j comma k. It is, we can write it within the bracket 1 or we can remove the bracket 1 in the superscript also. That is nothing but what is the probability that the system will be in the state k in n plus 1th step given that it was in the state j in the nth step. Here also j comma k belonging to capital S. So, this is the one step transition probability. So, our interest is to find out what is the distribution of x n. Whenever the sequence of random variable x n is a time homogeneous DTMC, our interest is to find out the distribution of x n. So, it has the probability mass function, the p j of n, that is nothing but what is the probability that the system will be in the state j at the nth step. So, the j is belonging to S and the n can be 1 or 2 and so on, because you know the distribution of n is equal to 0. That means, you know the initial probability vector of x 0. So, our interest is to find out what is the distribution of x n for n is equal to 1, 2, 3 and so on. So, how we are going to find out this distribution? So, this distribution can be written using the p j of n is nothing but the summation over I belonging to S such that the system was in the state I at 0th step and multiplied by what is the probability that it will be in the state j given that it was in the state I at 0th step. So, this is nothing but what is the probability that the system will be in the state j in the nth step. That is same as what are all the possible ways the system would have been moved from the state I from the 0th step to the state j in the nth step. So, this is the product of one marginal distribution and one conditional distribution for all possible values of I, that gives the distribution of x n in the nth step. So, for that you need to compute this distribution of x n, you need n step transition probability as well as the initial distribution vector or initial probability vector or the distribution of x naught. So, the distribution of x naught can be given as the vector p of 0. This vector p of 0, it consists of the element what is the probability that x naught takes the value 0, what is the probability that x naught takes the value 1, what is the probability that x naught takes the value 2 and so on. So, this is the initial probability vector. Why we have taken the state 0, 1, 2 and so on, unless otherwise as mentioned in the set of the state space, that is going to be the possible values of 0, 1, 2 and so on. This unless otherwise it is assume it, you can take always these values. So, this is the initial probability vector or initial distribution vector. So, what we need, what is the n step transition probability of the system will be in the state j given that it was in the state I at the 0th step. This is what we want to find out. What is the conditional probability mass function of n step transition probability vector. So, that we can write it in the form of p I comma j of superscript n, that is nothing but the probability of the system will be in the state j given that the system was in the state I at the 0th step. That is we need to compute the n step transition probabilities, that is p I j of n. So, this can be computed by using the method called Chapman-Kolmogorov equations. So, this Chapman-Kolmogorov equation provide a method for computing this n step transition probabilities. So, how we are going to derive this Chapman-Kolmogorov equation, that I am going to do it now. So, we are going to derive the Chapman-Kolmogorov equations for the time homogeneous discrete time Markov chain. So, let the p I j of superscript n, that is nothing but what is the probability that the x m plus n takes a value j given that x m was I. Since the discrete time Markov chain is the time homogeneous, so this is the transition probability of system moving from the state I to j from the mth step to m plus nth step. Therefore, this transition is the n step transition probability matrix for the time homogeneous discrete time Markov chain. Let us start with the 2 step. The 2 step is nothing but what is the probability that system is moving from the state I to j in 2 steps. So, n plus 2 takes the value j given that x n was I. This is for all n it is true, because the DTMC is disk time homogeneous. So, this probability you can write it as this 2 step transition probability of system moving from I to j, the state I to the state j in 2 steps, that you can write it as what are all the possible ways the system is moving from the state I to j by including one more state in the first step. The state is k given that the system was in the state I in the nth step for all possible values of k belonging to S. I can write this conditional 2 step conditional probability mass function from the nth step to n plus second step, that is same as I can include one more possible state of k in the n plus 1th step. Now, I can expand this as that is same as what possible values of k, and what is the probability that the system was in the state j in the n plus second step and the system was in the state k in the n plus 1th step, the system was in the state I in the nth step, divided by what is the probability that in the nth step it is in the state I. The numerator joint distribution of these 3 random variable, that I can write it as in the form of conditional what is the conditional probability that the x n plus 2 takes the value j, given that x n plus 1 takes the value k and x n takes the value I, product of x n plus 1 takes the value k comma x n takes the value I, divided by what is the probability that x n takes the value I, and here the summation is over the k. So, basically I am writing the numerator joint distribution of these 3 random variable as the product of a conditional distribution with the marginal distribution of those 2 random variable. Since the xi's are the time homogeneous Markov chain, this conditional distribution by using the Markov property is same as the conditional distribution of x n plus 2 takes the value j, given that only the latest value is important, the latest value is needed, not the previous history. Therefore, because of the memoryless property, x n takes the value I is removed. Therefore, this conditional distribution is the conditional distribution with only x n plus 1 with x n plus 2. And similarly, I can apply the joint distribution of these 2 random variable x n plus 1 and x n. I can again write it as the probability of x n plus 1 takes the value k, given that x n takes the value I, and the probability of x n takes the value I, whole divided by probability of x n takes the value I. So, this and this get cancelled. So, this is nothing but the conditional probability, this is nothing but the one step transition probability of system moving from k to j, and the second term is a one step transition probability of system is moving from I to k. Therefore, the left hand side we have what is the two step transition probability of I to j is same as all possible values of k. What is the one step transition probability of system is moving from I to k, and one step transition probability of k to g. So, this product will give the two step transition probability of system is moving from the state I to j, that is same as what is the possible values of k, the system is moving from the state I to k and k to j. So, this is for the two step. Similarly, by using the induction method, one can prove I to j of m plus 1 steps, that is same as what is the possible values of k, the system is moving from one step from I to k and m steps from k to g. This is a two step. So, this one step from I to k and one step from k to j. By induction I can prove the m plus 1 step will be I to k and k to j in m steps. Similarly, I can make it in the other way around also. It is I to k in m steps and k to j in 1 step also. That combination also will end up the m plus 1 step the system is moving from I to j. In general, we can make the conclusion the system is moving from I to j in n plus m steps, that is same as the possible values of k of probability of system is moving from I to k in m steps, and the n step the system is moving from k to j. That will give for all possible values of k, that will give the possibility of system is moving from I to j in n plus m steps. So, this equation is known as Chapman-Kolmogorov equation for the time homogeneous discrete time Markov chain. So, whenever you have a stochastic process is time homogeneous discrete time Markov chain, then that satisfies this equation, and this equation is known as the Chapman-Kolmogorov equations. In the matrix form, you can write the capital P is the matrix which consists of the element of one step transition probabilities. In that case, if you make m is equal to 1 and n is equal to 1, then the matrix of P of superscript 2, that is the in matrix form of a two step transition probability, that is nothing but if you put n is equal to 1 and m is equal to 1, you will get P into P, and that is going to be P square. So, the right hand side P superscript within bracket 2 means it is a two step transition probability matrix, and the right hand side P square, that is the square of the P matrix, where P is the one step transition probability matrix. So, in this form, in general you can make the n step transition probability matrix is nothing but P of n for n is greater than or equal to 1. For n is equal to 1, it is obvious. For n is equal to 2 onwards, the P power n, that is same as the n step transition probability matrix. Hence, so now we got the n step transition probability is nothing but the P power n, where P is the one step transition probability matrix. Therefore, in matrix form, I can give the P of n. The P of n is nothing but in the matrix form of the distribution of x n, or this is nothing but the vector which consists of the nth step where the system will be. So, this is nothing but what is the probability that in the nth step the system will be in the state 0, or in the nth step the system will be in the state 1, and in the nth step the system will be in the 2, and so on. This is the vector. So, the P of n you can find out in the matrix form by using the above equation. It is going to be P of 0, that is also vector, initial probability vector, multiplied by P power P of within bracket n, that is a n step transition probability matrix, but the n step transition probability matrix is nothing but the P power n. Therefore, this is same as the P of 0 into P power n. In the last slide, we got P of superscript within bracket n, that is a n step transition probability matrix is same as the one step transition probability with the power n. Therefore, this is going to be the distribution of x n in the vector form, that is same as the P 0 multiplied by the P power n, where the P is nothing but the one step transition probability matrix. That means, if you want to find out the distribution of x n for any n, you need only the initial probability vector and one step transition probability matrix. Because the discrete time Markov chain is the time homogeneous, we need only the one step transition probability matrix and the initial probability vector that gives to find out the distribution of x n for any n. So, with the help of one step transition probability matrix and the initial probability vector, you can find the distribution of x n for any n. Now, we are moving into simple examples using the n step transition probability matrix and the one step transition probability vector, how to find the distribution of x n for some simple example. The first example which I have discussed in the lecture 1, this is a very simple example in which the underlying stochastic process is a time homogeneous discrete time Markov chain with the state space S is 0, 1 and 2. So, this is the state space, and the information which we have Based on that, we can make a one step transition probability matrix, that is nothing but what is the possible probability in which the system is moving from the state I to j in one step, that you can fill it up. So, this exercise we have done it in the lecture 1, and now our interest is to find out, and also we have made the state transition diagram which is equivalent to the one step transition probability matrix, and we have got the state transition diagram. Now, the question is, if the system starts out with both the machines operating, what is the probability that both will be operation 2 days later? So, if you recall, what is the random variable? X n be the number of machines in operation at the end of the nth day. So, the random variable is how many machines are in the operation at the end of nth day. So, here the clue is at the time 0 or the 0th step, both the machines are operating. Therefore, x 0 is equal to 2 with the probability 1. So, the given information with the probability 1, both the machines are working at the 0th step. So, this can be converted into the P x 0 takes a value 2, that probability is 1, or we can make it in the initial probability distribution or initial probability vector as what is the probability that at x 0 the system was in the state 0, at the 0th step the system was in the state 1. So, this is the initial probability vector. So, at time 0 the system was in the state 2, therefore, that probability is 1 and all other probabilities are 0. So, this is the given information about the initial probability vector. Now, the question is, what is the probability that both will be operation 2 days later? That means, what is the probability that we can convert this into what is the probability that x 2 in the second step the system will be in the state 2, given that the system was in the state 2 at the 0th step. So, this is what you have to find out. What is the conditional probability? If the system starts with both the machines, what is the probability that both will be operation in 2 days later? So, not even this is a conditional probability. The question is, what is the probability that the system will be in the state So, to find this, you can make what is the probability that with the given information is there, x 2 is equal to 2, given that x naught is equal to I for all possible values of I. And this is same as, since the initial probability vector is going to be 0, 0, 1. So, this is land up. What is the probability that the x naught is equal to 2 multiplied by what is the probability that x 2 is equal to 2, given that x naught is equal to 2 and all other probabilities are 0. Therefore, 0 into anything is going to be 0. Therefore, it is same as what is the probability that x naught is equal to 2 and the conditional probability, and x naught is equal to 2 is 1. Therefore, this is same as what is the probability that x 2 is equal to 2, given that x naught is equal to 2. So, this is same as what is the probability that 2, 2 in 2 steps. This is nothing but the system was in the state 2 at 0th step and the system will be in the state 2 after the 2 steps. So, this is a 2-step transition probability of system moving from the state 2 to 2. This is same as you find out the p square matrix, and from the p square matrix this is nothing but the 2 comma 2, that is going to be the last element. Out of that 9 elements, the third row third column element, that is going to be the element for the this probability. So, what you have to find out is find out the p square, find out the p square. So, we have provided the p. So, this is the p matrix. So, from the p matrix you find out the p square. So, the p square is also going to be a 3 cross 3 matrix. So, from the p square 3 cross 3 matrix you take the third row third element, third column element, and that is going to be the probability for two-step transition of system moving from the state 2 to 2. That is going to be the answer for the given question. What is the probability that both will be operation in 2 days later? Similar to this, we can find out the probability for any day, for any finite day, by finding the p power n matrix, then pick the corresponding element, and that is going to be the corresponding probability. Now, we will move into the next example. This is abstract example in which the xn be the discrete time Markov chain. The default discrete time Markov chain is always, it is a time homogeneous. So, this is a time homogeneous discrete time Markov chain with the state space 0, 1 and 2, and also it is provided the initial probability vector, that is a p0, that is a vector that is 1/4 of 1/4. So, the summation is going to be 1. Therefore, this is the initial probability vector. That means the system can start from the nth 0th step with the probability 1/4 from the state 0, from the state 1 with the probability of, with the probability 1/4 it can start from the state 2, and also it is provided the one step transition probability matrix. From the one step transition probability matrix you can draw the state transition diagram also, because the state space is 0, 1, 2, therefore, the nodes are 0, 1 and 2, and this is the one step transition probability. Therefore, 0 to 0, that probability in one step the system is moving from the state 0 to 0, that is 1/4, and the system is moving from the state 0 to 1 in one step, that is 3/4, and there is no probability from the going from the state 0 to 2, therefore, we should not draw the arc. From 1, the one step transition probability of 1 to 1 is 1/3, and this is 1/3, and similarly this is 1/3. From the state 2, 2 to 0 is 0, and 2 to 1 is 1/4, and 2 to 2 is 3/4. This diagram is very important to study the further properties of the states. Therefore, we are drawing the state transition diagram for the discrete time Markov chain. So, this is a one step transition probability matrix, and this is the state transition diagram. Our interest is to find out the few quantities, that is what is the probability that x naught is equal to 0, and x 1 is equal to 1, and x 2 is equal to 1. What is the probability that the system was, it is a joint distribution of these 3 random variable, x naught is equal to 0, and x 1 is equal to 1, and x 2 is equal to 1. So, this is same as the joint distribution is same as, you can write it in the product of the conditional distribution, and the conditional distribution again you can write it using the Markov property, the conditional probability of only one step. Therefore, this is going to be by using the probability theory, you apply the joint distribution is same as the product of conditional distribution. By using the Markov property, you reduce it into the another conditional distribution. So, this is same as what is the probability that x2 is equal to 1 given that x1 is equal to 1 multiplied by x1 is equal to 1 given that x0 is equal to 0 and the probability of x0 is equal to 0. So, this is the first term is nothing but the one step transition of system is moving from 1 to 1, and this is nothing but the system is moving from the state 0 to 1, and this is the initial you take the probability from the initial probability vector of x0 is equal to 0. Now we are going to label the one step transition probability matrix with the 0, 1, 2 and 0, 1, 2. From this we can find out this is a one step transition probability of system moving from 1 to 1. So, 1 to 1 is 1/3 into this is a system probability of system moving from 0 to 1. So, 0 to 1 is a 3/4 and the system started from the state 0 in the 0th step. So, that you can take it from the first element, that is 1/4. So, if you do the simplification, you will get 1/60. So, this is the joint distribution of the system was in the state 0 at 0th step, the system was in the state 1 at the first step and the system was in the state 1 at the second step. That probability is 1/60. Similarly, you can find out the other probabilities also, that is suppose our interest is what is the probability that at the end of second step the system will be in the state 1. That is nothing but what are all the possible states in which the system would have been started from the state I, and what is the two step transition of system is moving from the state I to 1. So, the I is belonging to S. So, here the S is 0, 1, 2. So, already we have given the initial probability vector, that is 1/4 of and 1/4. Using this, and you need a two step transition probability, that means you need to find out what is the p square. So, the p square will give the two step transition probability matrix. Therefore, the p is provided to you. So, the p is 1/4, 3/4 and 0, 1/3, 1/3, 1/3, 0, 1/4, 3/4. So, this is the p. So, you multiply the same thing 1/3, 1/3, 1/3, 0, 1/4, 3/4. You find out the p square. So, from the p square you pick out the element of x0 is equal to for all possible I, then multiply this, and that multiplication will give probability of x2 is equal to 1. So, I am not doing the simplification. So, once you know the p square, you can find out probability of x2 is equal to 1. Similarly, one can compute the other conditional probabilities also. Suppose our interest find out what is the probability of x7 is equal to 0 given that x5 was 0. This is same as what is the probability that the system was in the state 0 in the fifth step, given that what is the probability that the system will be in the state 0 in the seventh step. That is same as what is the probability of what is the probability of 0, 0 in 2 steps. That means you find out the p square. From the p square, the 0, 0 is nothing but you take the first row, first column element, that is going to be the probability of x7, is equal to 0, given that x5 is equal to 0. Similarly, you can find out all other different conditional probability, and what we have to do is always you have to convert, because of the given DTMC is a time homogeneous. So, you converted into find out the n step transition probability, and n step transition probability is same as the p power n. So, you pick the corresponding element to find out the conditional probability. Now, we are moving into the third example. This example talk about the communication system in which whenever the transmission takes place with the digits 0 and 1 in the several stages. Now, we are going to define the random variable x naught be the digit transmitted initially, that is a 0th step. Either the transmission digit will be 0 or 1, therefore, only two possibilities can be takes place at any nth step transmission, either 0 or 1. Like that, we are making the transmission over the different stages. Therefore, this x n over the n will form a stochastic process, because you never know which digit is transmitted in the nth stage. So, each stage is going to be a one random variable, and you have a collection of random variable over the stages. Therefore, it is a sequence of random variables. So, this is going to form a stochastic process, and this stochastic process is nothing but the discrete time, discrete state stochastic process, because the possible values of x n is going to be 0 or 1. Therefore, the state space is 0 or 1, and it is a discrete time, discrete state stochastic process. The way the subsequent transmission takes place depends only on the last transmission, not the previous stages. Therefore, you can assume that this follows a Markov property. Therefore, this stochastic process is going to be called it as a discrete time Markov chain. Now, our interest is to find out. So, now I will provide what is the one step transition probability for the Markov chain, or let me give the transition diagram for that. So, state transition diagram, the possible states are 0 or 1, because the state space is 0 and 1, and the probability that in the next step also the transmission is 0 with the probability 1 minus a. This is a conditional probability. This is the conditional probability of the nth stage the transmission was 0, the n plus 1th stage is also the transmission is 0 with the probability 1 minus a. The one step transition probability of system is moving from 0 to 1, that probability is a. That means, the nth stage the transmission was digit 0, the n plus 1th stage also the n plus 1th stage the transmission will be the digit 1 with the probability a. Similarly, I am going to supply the one step transition probability of 1 to 1, that is 1 minus b, and this is b. That means, this 1 to 0, that probability is 1 to 0 is b, and 1 to 1 is 1 minus b. Obviously, this a is lies between 0 to 1, and b is also lies between 1. So, this is the a is the probability that the system is transmitting from the 0th step nth stage with the digit 0, and the n plus 1th stage with the probability with the digit 1, that probability is a. Therefore, the negation is 1 minus a, because this system can transmit either 0 or 1. So, once you say that the one step transition probability of 0 to 1 is a, then 0 to 0 will be 1 minus a. Similarly, 1 to 0 is given as a probability b, and the other digit transmission will be 1. Therefore, it is going to be 1 to 1 will be 1 minus b. So, this is the state transition diagram, and this is the one step transition probability for a given time homogeneous discrete time Markov chain. Our interest is to find out what is the distribution of xn for n. For that you need what is the n step transition probability matrix. Since the one step transition probability matrix is given, you can find out p square, p power 3 and so on. By induction method you can find out the p power m, but using the p power m you can find out the p m plus n. Therefore, you can come to the conclusion what is the n step transition probability of system is moving from 0 to 1 and to 0 to 0 and so on. So, this is nothing but I am just giving the only the result b plus a times 1 minus a minus b power n divided by a plus b, and this is nothing but a minus a times 1 minus a minus b power n divided by a plus b. Similarly, if you find out the n step transition probability of system moving from 1 to 0, that is b minus b times 1 minus a minus b power n divided by a plus b, and this is nothing but a plus b times 1 minus a minus b power n divided by a plus b. So, here I am just giving the n step transition probability in matrix form. By given p, you should find out the p square, p power cube. By induction you can find out the p power n, and this is valid provided 1 minus a minus b which is less than 1, because you are finding the p power n matrix. So, here it needs some determinant also, unless otherwise the absolute of 1 minus a minus b which is less than 1, this result is not valid. So, provided this condition, the p of n, that is the matrix. So, that is same as p power n also. P of n is same as p power n. So, as n tends to infinity, you can come to the conclusion what is the probability that the system will be in the state 0, that is same as b divided by a plus b, and similarly what is the probability that the system will be in the state 1 as n tends to infinity, that will be a divided by a plus b. This can be visualized from the state transition diagram easily. Whenever the system is keep moving into the state 0 or 1 with the probability a, b and with the self loop 1 minus a and 1 minus b, the subsequent stages the system will be in any one of these two states. So, with the proportion of b divided by a plus b, the system will be in the state 1. Similarly, with the proportion a divided by a plus b, the system will be in the state 1. With the proportion b divided by a plus b, the system will be in the state 0 in a longer run. The interpretation of as n tends to infinity, this probability is nothing but in a long run with this proportion, the system will be in the state 0 or 1. So, this state transition diagram will be useful to study the long run distribution, or where the system will be as n tends to infinity. To study those things, the state transition diagram will be useful. Now, we will move into the next problem, that is example 4. Let a sequence of random variable be a sequence of independent random variables. With condition the probability of yn takes a value 1, that probability is p, that is same as 1 minus the probability of yn takes a value minus 1. We have a stochastic process and each random variable is a independent random variable, and the probability mass function is provided with this situation. The probability of yn takes a value 1 is p. You can assume that the p takes a value 0 to 1, that is same as 1 minus of probability of yn takes a value minus 1 for all n. Now, I am going to define another random variable. Let xn be defined by x naught is equal to 0, whereas x n plus 1 onwards, that is going to be x n plus y n plus 1 for n is equal to 1, 2 and so on. So, we are defining another random variable x n with the x naught is equal to 0 and x n plus 1 is equal to x n plus y n plus 1. Now, the question is, check x n, that stochastic process is the DTMC. If it is a DTMC, also find out what is the probability of x n takes a value k. We started with one stochastic process and we define another stochastic process with the earlier stochastic process, and check whether the given the new stochastic process is a discrete time Markov chain, that is a default one, that is a time homogeneous discrete time Markov chain. If so, then what is the probability of x n takes a value k? That is nothing but find out the distribution of x n. So, how to find out this? The given or the x n is going to be the DTMC. Since y n takes a value 1 with the probability p and y n takes a value minus 1 with the probability 1 minus p, you can make out the possible values of y n is going to be 0 or plus or minus 1, plus or minus 2 and so on, because the relation is x naught is equal to 0 and x n is x n plus y n plus 1, and the range of y n is 1 comma minus 1. Therefore, the range of x n, that will form a state space and x naught is equal to 0. Therefore, x n, that relation is x n plus 1, x n plus 1 is equal to x n plus y n plus 1. So, n takes a value 1 and so on. Therefore, the possible values of x n will be 0, plus or minus 1 or plus or minus 2 and so on. Therefore, that will form a state space. Now, the given clue is probability of y n takes the value 1 is probability p, and the probability of y n takes the value minus 1, that is 1 minus p, and the probability p is lies between 0 to 1. So, using this information you can make a state space of the y n, that is going to be 1, 2 and so on, minus 1, minus 2 and so on. Now, we can fill up what is the one step transition of system is moving from 0 to 1. That means, the x 1 0 to 1, suppose you substitute 0 here, then suppose it takes a value 1 then the system can move from the state 0 to 1 in one step. Suppose you put the value x naught x n is equal to 0, suppose you put x n is equal to 0 and y n plus 1 takes a value 1 with the probability p, then the x n plus 1 value will be 1 with the probability p. Correct. Now we can go for what is the state transition probability of 1 to 0. Suppose the x n value was 1, suppose the y n plus 1 value was minus 1, then the x n plus 1 value will be 0. So, the one step transition of a system moving from 1 to 0 because of happening probability of y n plus 1 is equal to minus 1, that probability is 1 minus p. So, this is going to be. So, whenever the system is moving from one step forward, that probability will be the probability p, and one step backward, that probability will be 1 minus p. So, this is the way it goes forward step, and this is the way it goes to the backward step. So, you can fill up all other probabilities, forward probability with the probability p and the backward probability with the 1 minus p. Also, we can come to the conclusion, the way we have written x n plus 1 is equal to x n plus y n plus 1, and all the y i's are independent random variable. The x n plus 1 going to take the value depends only on x n, not the previous x n minus 1 or x n minus 2 and so on. Therefore, the conditional distribution of x n plus 1 given that x n minus 1 till x naught, that is same as the conditional distribution of x n plus 1 given x n. That means, the x n is going to satisfy the Markov property because of this relation, because of x n plus 1 is equal to x n plus independent random variable. Therefore, the x n is equal to 1, 2, 3 and so on, this stochastic process is going to satisfy the Markov property. Therefore, this discrete time discrete state stochastic process is going to be the discrete time Markov chain because of the Markov properties satisfied. Once it is Markov property satisfied, by using the Chapman-Kolmogorov equation, you can find out what is the distribution of x n takes the value k. That is nothing but where it started at time 0 and what is the conditional distribution of n step transition probability, and the n step transition probability is nothing but the element from the p power n, and from here you can find out the one step transition probability matrix. From the one step transition probability matrix you can find out the p square, p cube and so on, and you can find out the p power n, and that element is going to be the n step transition probability. Using that you can find out the distribution, and since we do not know the value of p, where p is lies between 0 to 1, it is I am not going to discuss the computational aspect of finding out the distribution. This is left as an exercise and the final answer is provided. The difference between the earlier example and this example, the state space is going to be a countably infinite. Therefore, the P is not going to be a easy matrix, it is going to be a matrix with the many elements in it. Therefore, finding out the P square and the P power n, it is going to be little complicated than the usual square matrix. So, hence the conclusion is by knowing the initial probability vector and the one step transition probability matrix or the state transition diagram, we can get the distribution of x n for any n. There is a small mistake, the running index for x n plus 1 value is equal to xn plus yn plus 1, that is starting from 0, 1, 2, and similarly the previous slide xn plus 1 is equal to xn plus yn plus 1, and n is running from 0, 1, 2, and so on. So, in this lecture we have discussed Chapman-Kolmogorov equation, and also we have discussed the n-step transition probability matrix. So, the n-step transition probability matrix can be computed from the one-step transition probability matrix with the power of that n. And also we have discussed 4 simple examples for explaining the Chapman-Kolmogorov equation and the n-step transition probability matrix. For the lecture 1 and 2, we have used these 3 books for as a reference. The first one is J. Mehdi Stochastic Processes book, and the second one is Kishore Trivedi Probability and Statistics with the Reliability, Queuing and Computer Science Applications. The third one is Shelton Ross Introduction to Probability Models. So, with this I complete the lecture 2 of discrete time Markov chain. Thanks.